Good morning friends. Today we are going to discuss about genetic equilibrium. What is the genetic equilibrium? Before dealing with the genetic equilibrium, a common term we have to familiarize, that is the Mendelian population. What is actually Mendelian population? Mendelian population. Mendelian population means a group of interbreeding individuals, a group of organisms that interbreeding among themselves. So that is called a group of interbreeding individuals is known as the Mendelian population. The most extensive Mendelian population is the humankind. Human. So humankind can interbreed with each other. And that interbreeding population group is known as the Mendelian population. Any group that interbreed with each other and forming a group that is known as the Mendelian population. So most extensive Mendelian population is the human population, and the human Mendelian population also have many sub-Mendelian population or geographical populations. See, that is the Mendelian population. Then two scientists, that is in the year 1908, that is W.H. Hardy and W. Weinberg. These two scientists proposed the frequency of the genes in the Mendelian population. Number of genes, number of alleles, frequency of the alleles of the genes in the Mendelian population. And they proposed that the frequency of the genes in the Mendelian population can transfer from one generation to the another generation without any change. That is known as the genetic equilibrium. Suppose this is the Mendelian population, and this Mendelian population have number of the genes, and the frequency of these genes cannot change when it transfer to the next generation. So generation number was first. And similarly, from the next generation, that is a generation number third, the frequency of the genes in this population cannot change when transferring to the generation to generation, and this is known as the genetic equilibrium. Genetic equilibrium. Genetic equilibrium. And Hardy and Weinberg proposed a principle saying that the gene's frequency cannot change from transferring from one generation to another generation. That is known as the Hardy-Weinberg principle. So genetic equilibrium, Hardy-Weinberg principle. So Mendelian population having a particular percentage or the frequency of the alleles. The frequency of the alleles cannot change from transferring from generation to generation. That is known as a genetic equilibrium. And the principle proposed by the Hardy and Weinberg related to this genetic equilibrium is known as the Hardy-Weinberg principle. See here, when the characters or the genes transferring from, or the frequency of the genes cannot change from generation to generation, but there is a condition. Random mating must be taken place. So far as random mating taken place, and no mutation is happening, and no natural selection is happening, and no choice. In that condition, the gene frequency cannot change when transferring from generation to generation. So according to the Hardy-Weinberg, the equilibrium or the gene frequency cannot change unless if no mutation taken place and no natural selection and no choice is there. So based on this, these two scientists, Hardy and Weinberg, proposed a theory that is known as the Hardy-Weinberg theory. Okay, so then these two scientists again proposed an algebraic formula for this theory, regarding to this theory, that is known as the Hardy-Weinberg formula. So suppose let us derive the Hardy-Weinberg formula, how to reach the Hardy-Weinberg formula. So suppose in a population there are three alleles. Take the three alleles like this. In a population, there are three alleles. So what are the three alleles? One of the allele is capital A. Another allele is a capital A, small a. Another allele is a small a. So these are the three alleles. Okay, and these three alleles are occurred in the ratio 1:2:1. Okay, and out of this, the allele A is a dominant over A. So A is a dominant and a small a is a recessive. So suppose a population having three alleles, capital A, capital A, small a, and small a, small a, in the ratio 1:2:1, in which the capital A is a dominant over small a. Okay, so this is the one type of the population. In this population, the genes alleles are present like this. Then let us see how these alleles transfer to the next generation without changing. Why not changing? Because there is no mutation, there is no natural selection, and there is no choice, and random mating is taken place. So how it transfer to the next generation without changing? See how the Hardy-Weinberg proposed this, explained this one. Suppose, so this is the A, and this is the A, small a, and this is the A. This is the male, random mating taken place. This is the A, this is the A, and this is the A. So during the random mating, it producing the gamete A. It producing the gamete A and A. It produces the gamete A and only A. All the gametes are similar. And it also producing the gamete A. It producing the gamete A and A. It producing the gamete A. So these are the gametes. It produces two type of the gamete. One is the capital A, another is the small a. It producing all the gamete capital A. It producing all the gamete small a. It is the again capital A, and a small a. It producing all the gametes are the A. So how the random mating taken place? This mate with this one and producing the capital A. This mate with this one, so it producing capital A and capital A and small a, and this with this one and producing capital A and small a. This mate with this one and producing capital A and also capital A and small a, like this. And similarly here, this A mate with this one and capital A and A with the small and capital A, small a, and small a with this one and small a, like that. This also mate with this one, so capital A and small a, capital A and small a, and small a, like that. This mate with this one, so capital A, small a only, and this mate with this one and producing capital A, small a, and small a, and this with this one it producing capital A, small a. So here 1/16 is capital A, small a, and this is the 1/16, and this is again 1/16, and this is again 1/16. This is again 1/16, this is again 1/16, 1/16, 1/16, again 1/16, this is 1/16, this is 1/16, this is 1/16, again 1/16, and 1/16, and 1/16. So here the ratio capital A and capital A, small a, and small a, the ratio is again 1:2:1. So this prove that the law is correct, that is when the transferring the one generation, the genes are transferring from one generation to another generation, population transferring from another generation, the ratio cannot change. This is known as the genetic equilibrium. Okay, so this is concerned with the population. So let us take the genes, gene frequency, how it is happening, how it is transferring from one generation to another generation. During the transfer also, the gene frequency also not change. Suppose the gene frequency, the frequency of the A in the population, gene frequency A is 50%, and its frequency of the small a is again 50%. So this 50% means 0.5, and this is again 0.5. So how it is changing? It cannot change. As per the Hardy-Weinberg principle, this frequency cannot change when transferring from one generation to another generation. That is a genetic equilibrium. See here how it is happening. Suppose a cross like this. This is the capital A, it is a 0.5%. This is the small a, it is a 0.5%. Again, this is the capital A, 0.5%. This is the small a, 0.5%. So A means it is A means the ratio again 0.25. This is A again 0.25. This again 0.25, this again 0.25. So see here, this is A is 0.25, and capital A and small a. So this is AA, that is 0.25 is 0.5, and small a, capital A, small a, and this one capital A, small a. This is capital A and small a. This again capital A, small a. So this again 0.25. So here the ratio again 1:2:1. So during the transfer of the one generation to another generation, the gene frequency also not changed. Okay, and similarly, we are now talking about the population and the gene frequency. So now we take about the genetic or the genotypic frequency. What happens for the genotypic frequency? The genotypic frequency also not changed. So how it happens here, the genotypic frequency. Suppose the frequency of the allele capital A, that is the Q, that is equal to 1. And the frequency of the small a, that is equal to P, that is equal to 1 minus Q. 1 minus Q. Okay, this is the frequency of the A is a Q, and the frequency of the small a is equal to P, that is equal to 1 minus Q. So how it happening the inheritance taken place? See here, let us take a chart here. This is the P, sorry, this is the Q, A, Q, that is the A, and this is the P, that means 1 minus Q. And similarly, this is the Q, A, and this is the 1 minus Q. So see here, this is the Q square A. So here, this is the Q1 minus Q A. And here again, this is the Q1 minus Q A. And here is again 1 minus Q whole square. So here again, the ratio 1:2:1. This ratio is maintained. So during the genotypic transfer, if you consider with the genotype also, the gene ratio or the genetic equilibrium is maintained. So if it is a population or the gene frequency or the genotype, in all these conditions, the frequency is maintained from generation to generation, and this is known as the genetic equilibrium. And it is proposed by Mendel, proposed by the Hardy and Weinberg, and so it is known as the Hardy-Weinberg principle. And the formula for the Hardy-Weinberg principle is, that is the P square plus 2PQ. This is the 2PQ, this is the Q square, this is the Q square, and plus this is equal to P, that means P square is equal to 1. Q square plus 2PQ plus P square is equal to 1. This is known as the Hardy-Weinberg general formula. Algebraic formula is prepared by Hardy-Weinberg, and this is known as the Hardy-Weinberg formula. So based on this Hardy-Weinberg formula, number of the questions will ask for the NEET examination. I took already 3 examples here. How to solve these problems based on this Hardy-Weinberg principle. Remember that A plus A is equal to 1, or A square plus small capital A square plus small a square is equal to 1. And similarly, if you take the Q square plus P square, that is equal to 1, or when it is expanding, Q square plus 2PQ plus Q square is also equal to 1. This is called the general formula prepared by, proposed by Hardy and Weinberg. So based on this formula, number of the questions asking for the NEET examination. Let us see a few questions related with this formula. So first question is already written on the blackboard, that is the frequency of the 2 alleles in a gene pool is 0.9. A frequency is 0.19, and the frequency of the small a is equal to 0.81. So the question is, calculate the percentage of the heterozygous individual in the population. So what is a heterozygous individual? Q square plus 2PQ plus P square is equal to 1. This is the heterozygous individual, and this is the homozygous or dominant individual, and this is the homozygous or recessive individual. So the question, what is the percentage of the P and Q of heterozygous individual. Calculate the percentage of heterozygous individual in the population. So we already know that what is the P value of the P is already given, that is the 0.19, and Q is equal to 0.89. So what is the value of this? 2PQ, 2 into 0.19 into 0.89. So that is equal to 0.66. So 0.66 is the percentage, or if you count in the out of 100, it is 66 percentage. Heterozygous is a 66 percentage. So like that, what is the homozygous percentage? Homozygous percentage means P square. P square means 0.81 into 0.81. So that is equal to 0.81 into 0.8. No, this is wrong. This is equal to 0.31, that is equal to 31 percentage, and this is equal to 0.6, that is equal to 66 percentage. So that is the heterozygous individual percentage and homozygous individual percentage. So let us take another example for here. That is the an allele W, capital W, allele capital W for white. This is the white and dominant over the allele small w, that is the black. Okay, so in the sample there are 9,900 sheep. Total sheep is 900. Okay, so out of that 891 is white and 9 is black. Okay, so the question is calculate the allelic frequency within this population, assuming that the population obey Hardy-Weinberg principle. So W is equal to, small w is equal to Q, and capital W is equal to P, and what is the value? What is the value of Q and P? What is the value of the P? So here Q square is equal to black, and P square is equal to white. So let us take like that. So number of the individual, black is actually 9. Total black is already given 9 individuals. So number of the individual divided by total number of the individual, that is equal to 9 upon 900. 9 upon 900, that is equal to 0.1. So 0.1, that is the Q square. So Q square we got, that is a 0.1. Okay, then Q is equal to Q square. And Q is equal to square root of the Q square, that is equal to square root of 0.1. So the square root of 0.1 is equal to 0.1. So this is actually 0.1. This is 0.1. So square root of 0.1 is equal to 1. Equal to 0.1. So Q, we got the value Q, that is the 0.1. Okay. Then we know that P plus Q is equal to 1. So therefore P is equal to 1 minus 0.1. So that is equal to 0.9. So we got the value of the Q is equal to 1 and P is equal to 0.9. So that is the question. Calculate the allelic frequency within this population, assuming the population obey the Hardy-Weinberg principle. Okay. So the next third question. So the third question, in a population that is Hardy-Weinberg equilibrium, the frequency recessive homozygous genotype of the certain trait is a 0.09 recessive. Calculate the percentage of the individual homozygous for the dominant alleles. So given Q square is equal to 0.09 percentage, and therefore the Q is equal to 0.09, that is equal to 0.3. So this is the frequency of the Q. So similarly, we know that P plus Q is equal to 1. So P is equal to 1 minus 0.3. So that is equal to 0.7. So got this one. So homozygous dominant. Homozygous, what is the question? Homozygous dominant. Homozygous homozygous dominant is equal to p square, that is equal to 0.7 square, that is equal to 49%. So 49% individual homozygous dominant is 49%. So like that, the questions may ask for the NEET examination related with the p square plus 2pq plus a q square is equal to 1. So the first p square is a dominant and 2pq is the heterozygous and q square is the recessive. Okay, so the maximum problems are related with this genetic equilibrium.